Hi everyone, and welcome to part 2 of the PhD thesis overview. So this is my PhD thesis called Towards Fast and Adaptable Agents via Goal-Directed Memory-Based Learning. It was done over 5 years with my supervisor, Prof. Mehul Botani. And yeah, last week I was sharing about the initial parts of the thesis, whereby we basically want to see how the human brain learns fast and adapts fast and impart all these insights from human connection into AI systems. So last week we covered DropNet, break tic-tac-toe, hippocampal replay, and learning fast and slow, which basically led me to figure out this path whereby, if we just focus on reward, it might be a little hard to generalize because the reward may not change over time. And the environments are typically quite static. So if we want to learn across environments, be more general, we might need to use goal-directed learning. So instead of learning from rewards, we learn from goals. And this would be a little more generalizable because, as your wants and needs change, you can just change your goal. And because you do not train on reward per se, you do not need to relearn from scratch again. You already have some sensing of the world. And I mean, this is apparent in like some studies about rats and mazes. They realized that rats actually could map out the maze even without food as a reward, which kind of shows that our brain, I mean, assuming that we are similar to rats, our brain has some function to learn from just our experiences alone, the goals that we have imparted in our brains. We can learn from those, and this can actually generalize across tasks, even differing tasks. So this is the recap for reinforcement learning. So we have an agent here. Agent takes a state, and basically agent has a state that is given to it. So the state could be something like a grid position, like the 0, top left position. It can take an action right, and the environment can say that, okay, now because you have taken an action right, you are now at 0, 1, and then your reward is 0. Okay, so environment reward typically is given with respect to a goal, usually. Like, for example, a game, a reward of 1 means you win the game. Reward of -1 means you lose the game. So actually, in a lot of reinforcement learning systems, the reward is a proxy for a goal. It's just that that goal is more or less unchanging. So we're just changing this reward term into more goal-directed term, make it a bit more natural and easier to generalize. And this was the slide I covered last week, where the basic insight is that because reward modeling, you kind of need to do by temporal difference learning. Whenever you have a certain value for a state or value for a state action pair, you need to update this value with this R plus gamma vs prime. This is actually the one step look ahead. So basically, based on what you experience for your next transition, you update your current estimate of the state value. So this actually has been shown to occur in the brain because we do temporal prediction in the brain as well. So this basically is guaranteed to reach optimality in the long run if your rewards don't change. But it's very, very slow to learn. Basically, whenever you have a path, you want to update the reward, you need to go from the end, update one time, update another time, and so on. You need to update this entire pathway. So this value-based reinforcement learning can be very slow to learn. And whenever your reward changes, let's say your door reaches on the bottom left instead of the bottom right, you kind of need to relearn all this look ahead again. So this is what is not very good with current RL methods. So fast and slow was a method that designed to just go directly to the goal, right? So when given your start state, like maybe 0, 0, and your goal state, maybe it's 4, 0, and then based on what we have learned before, maybe we can predict the action down or something. So this learns from your experience trajectories or your planned trajectories. So I'm not going to go through the details. Just look at the previous video for more info. But this is basically learning via unsupervised or self-supervised learning, where we can learn from our own experiences and then buff up our own predictions. So I believe that actually humans do this a lot. We observe a lot of data. We observe our own behavior, so our own state, our own goals, and our own actions. And actually, I also think that we can also observe other people's behavior and come to model their action as well. So that's how we do imitation learning. So these are very, very powerful ways to learn because you can learn from the environment directly without any ground truth, right? So this is the fast neural network. The slow neural network basically, the slow memory retrieval path is basically planning via multiple parallel simulations. So each branch will simulate the memory, and I liken this to like the mini columns in the neocortex. Each branch will simulate the trajectory from the state to the goal by referencing or stored transitions in memory. So the stored transitions in memory could be something like state, action, state prime, which is like when you go to like maybe the state is 0, 0, the action is down, and then the new state is 1, 0. So you store this kind of transitions. Whenever you have an initial state 0, 0, you try to reference all the memories that have a start state 0, 0. You randomly sample from it, and then you go to the next state and so on. And you keep doing that until you hopefully reach the end goal, which is like maybe 4, 0. So again, this is a bit slower because it takes time to do the look ahead, but it's also more accurate. And whenever there's an environment change, you can update your memory to incorporate new changes in environment instantly. So you do that by just replacing the memories that are wrong, the transitions that are wrong with the correct ones. Or, I mean, in future work, likely what I'll experiment with is that I will decay the memory such that, you know, if your memory is wrong, then it will be placed lesser importance so that we will prioritize retrieving those memories that are more important, which is like the newer memories. So yeah, this is just some ideas. Okay, so yeah, I think that's more or less the recap for part one. Do I want to ask anything or clarify something before we move on to what I want to cover today? All good? Okay, let's move on to part two then. So the first one is actually the work that I did about 2 years ago. This is work that was done on the ARC-AGI corpus, which is the using the ARC challenge, the abstraction and reasoning corpus challenge. Try to find out how can we imbue like large language models into the pipeline to process this kind of arbitrary abstractions and come up with patterns, like come up with the rules. Okay, let me just give the example here. So basically, when given the top diagram, we need to find out the rule that maps to the bottom diagram like that and like fills up the, like maybe in this case, the rule is to fill up this hole with yellow color square. So as long as you have an enclosed area, you fill up with the yellow square. So we don't tell the program what the rule is. We just give the input-output examples, and the program needs to figure out on its own how to do this arbitrary mapping to the test set. So this is a difficult challenge because every single ARC-AGI problem is has a different concept, or at least they strive to have a different concept. So it can be quite hard to learn from the previous previous example problems to give you the processing rule for the new one. You have to actually do some form of pattern matching and identify the patterns on the fly based on the training examples here. And hopefully you can find out the pattern and apply it to the test example. So this actually, I would say that ARC-AGI challenge is actually not exactly a challenge that mimics how humans think in the real world. In the real world, there's actually a bit more complex things to model. Like in real world, you actually have a bit of you need to model the temporal aspects where like you take action, you take a state, you do an action, and then you get a new state, and then you take another action, and then you get another state. Yeah, so ARC-AGI is a bit more static. Like you don't really see what happens as a result of your action because you're just predicting the state of the of a new situation. Yeah. So something like this where you actually have to do actions and go through states. I think that is a bit more reflective of the way humans actually think and learn from the environment. This one here is more of like pattern matching. Yeah, so actually ARC-AGI to me is a pattern matching test to see like whether you can, given certain rules, figure out those rules. Yeah, but also it's a bit conflated here because Francois Cholet did not give the rules directly, so it's more or less a guessing game about what rules can be encoded in here, right? So for this work, I actually discovered that, just giving the grid itself, let's say the grid is like this. We have 3 rows and 3 columns. And like, if we just give the grid colors directly like this, right, it may not solve a lot of problems because like it's constrained to this 2D view. So notice that I did not use numbers here, because if I use numbers, the LM might think it is a math problem. So I changed it to letters so that it biases the thought to remove away the bias of numbers being like modulo or addition or subtraction and so on. So I use letters, and like a dot is an empty square. So other than that, I also did object views, whereby instead of just giving the grid itself, I already categorize certain cells together. Like for example, this 3 red cells will be categorized as one object here. And then we have another 2 more cells here, will be characterized as another object here. And the last cell would be categorized as the last object here. Yeah, so basically this is a way to, help the model focus on the representation of continuous cells with the same color together as an object. Of course, there are various ways to do it with multicolor cells, with cells with diagonals. I mean, because right now the objects are only connected in like either horizontally or vertically. You can also define objects as connected via diagonal. Yeah, so this, of course, is a bit more constrained because like the moment your object does not conform to this kind of criteria, the kind of representation might fail. But with this representation, it solves a lot more problems. Okay. Of course, the last representation I use is basically based on color. Like I group all the same colors together. This is one color, this is one color, this one color. Because some problems require manipulation of color, like you change all of one color to another color and so on. So this pixel view will capture such changes. So in all, these representations capture a certain characteristic of rule change, right? So it is very, very similar to like how the visual cortex kind of processes information, in the sense that like for visual domains, we have stuff like depth perception, we have stuff like motion perception, color perception. So you can see that we don't actually process the entire image at one go. I mean, we do have a way to process the entire input stimuli, but it's normally broken down into distinct pathways. And I'm trying to mimic this because I feel like if you process into distinct pathways, you learn better. Like the analogy is like this. If I give you, I mean, for learning, I give you the entire world's knowledge to learn, and then you don't know how to process it. Like I don't tell you how to process it, and then I ask you to come out with an output. Like it may not be that great compared to if I give you like, okay, you learn via module A, you learn via module B. I already predefine the scope of your learning. So if I predefine your modules like that and then ask you to output something, you might learn better. So this is called constrained learning. You learn within the constraints of the system that I give you. Yeah. So the question that I always have to ask myself is that, like right now in this work, of course, this work is very preliminary. I might extend this work in the future. The question that I ask myself is, can we actually learn how to represent this like without even fixing it? And I mean, the work that most people normally think about when you learn about flexible rules to like map the input, people normally think about convolutional neural networks because, you learn the filters by the data itself. So, I mean, it could be possible that you learn the representation via lots of data if you have lots of data. The problem with the ARC challenge is that you don't really have that much data. So, the representations, if you give some kind of like bias to it, it will learn much better with the limited data that it has. But of course, if you have a lot of data, you might be able to learn like what are the best representations to do purely from the data itself. So this is something about like nature versus nurture. Should you start off with already a fixed representation, or should you like learn everything end to end? And actually, my view on this is that, it's good to have some bias, right? Because you will learn faster. Yeah, that's it. So if you can have the world's data of ARC challenge and like millions of problem sets and so on, then maybe a full end-to-end is good enough. You can fine-tune your model on a full end-to-end and it can learn how to do the problems itself. But without that, having some bias would actually greatly help to improve the solve rate. Yeah. Okay, so we move on to the process. So actually, this is a simplified view of what I've been presenting before in the past. So we give the training examples like the input-output pair. We transform it according to either the grid, pixel, or object view, or a combination of all of them. We do a chain of thought prompting with certain functions that are already used, like already predefined. So there's also some bias here in the action space. And notice that I use Python code here because I've experimented before. If we ask the LLM to just generate like text based on what rules there is to transform the object with, basically just talk in language. So if we ask the LM to describe the rule, like for example, shift the objects one square to the left. What I found out is that LMs don't really faithfully replicate this in the test rule, because this is just purely token prediction, next token prediction and like pattern matching kind of thing. It doesn't faithfully execute the rule. So in order to have a faithful or reliable execution, it's better to execute in code. So this actually was an insight that I got, and I was very surprised that O3, I don't think they have any code generator or code executor, and they managed to solve up like 80+% of ARC, and that is quite surprising to me. So it's either that O3 has memorized quite a lot of the test set, or that maybe it's a better model that is more faithful. I don't know. But as for what I've tested on GPT-4, you kind of still need to use some form of code in order to get more reliability. Okay, so just to give a summary of this again. So what I wanted to do was basically from the ARC training examples, give it different ways to pre-process it. And then after that, I basically ask it to generate a description of what it thinks the rule is in words. All right, in words. And then after that, I ask the LM to use whatever information it has from the earlier pipeline to generate out a Python code. Okay. After that, we do have some other pipelines like, we execute the code out in the environment, we check whether it's correct. Okay. And then, we can actually get some feedback, based on whether or not this code works for your training examples. Check whether code works on training examples. Yeah, so we have all these things that, you could do the environment feedback and so on, so that you can incorporate the error here to generate better code and so on. So I realized that this iterative feedback loop is actually quite important for, I think it solved about 8 problems of the 111 problems I tried. Yeah, so this environment feedback loop can actually help to improve the solve rate. And I think this environment feedback loop is great because this mimics the actual, actual real world environment better. I mean, the real world environment, you're not going to solve an IQ problem, right? To do one single pattern match. You will do an action, like maybe you will say that, okay, this is the pattern. You will get some feedback from the environment to tell you, hey, actually what you did was wrong, or what you did was correct. I think the main thing about learning is how you learn from feedback. I don't really care how you, can get the pattern in few shot or what. You need to learn from the feedback of the environment. You need to modify your learning procedure, modify your memories and so on. And this is something that I think it's very, very important. So actually, this artwork is incomplete. There's still one aspect that I haven't really had the time to do it, but I might do it soon. So this is the work where you store memories of what you have solved before and use it to solve future problems. So you could store successful problems in one memory. You could store unsuccessful problems in another memory, and whenever you have a new problem, you might incorporate the earlier kind of memories. Okay, however, there is a catch to this. Okay, because LMs don't do very well with long contexts. So you kind of need to select very, very precise and relevant memories to ground it. Okay, and also there's a risk if you put too much memories in there, you might end up making the LM be confused and think that your memories is actually the main problem, and it might output something different. So this is something that I have yet to experiment with, but I do think if we have memories and you can learn from what you have done before and do it into something new, then that will be a form of adaptive learning. And that's something more interesting to me than the ARC challenge. Yeah, so this is something that I'm exploring. Right now I'm doing some experiments on like making agents play the Squid Game. So okay, I'm not sure if you watch Squid Game, but like how it can learn from other agents' behavior to update its own memory and not make the same mistake again. Yeah, so that is something that I'm looking into because it's quite interesting to see how agents can learn from their own past behavior and learn from other agents' behavior. So yeah, more on that soon when I get the experiments out. Yeah. Questions or comments on this process? Okay, so if there's nothing, I'll move on. So this is the chain of thought prompting that was used. First, we will do some reflection on the answer. Like this is basically if we have a previous solution, a previous code that did not work. So we give the code, reflect on the previous code plus the error message, or plus the plus some plus the plus reflection on difference between code and code and code output and actual output. So this was the initial version that was used. Okay, so this enabled you to do like chain of thought. Oh, sorry, this enables you to do iterative thinking, whereby you can think about what happens before and try to improve it. Okay, but I realized something, when I keep doing this, like if I tell them the difference between the code output and actual output, it might actually get confused. So I actually changed this. Instead of difference between code output and actual output, what I actually did was I made the previous code output the start state, and then I basically asked it to reflect how to get to the end state. Okay, so this one actually, it's recently I've been reading a paper called Algorithm of Thoughts, where basically they ask the LLM to do chain of thought thinking to reach the end goal. And what happens is that as the LM goes through the different states and keeps thinking about how to get to the end goal, what we'll do is we'll take the previous states and we'll summarize them so that we get a more concise view of what happened before. And the LM can perform better after you summarize the previous states. So I realized a similar thing for this ARC challenge. If we do some form of summary, okay, or rather in this case, we just make the previous code output the start state. Okay, this is a bit confusing, but let me just explain what I mean. Let's say if this is my goal state. My goal state is I want 2 red squares at the top. So this is my goal state. If my initial state is like this, or this is the iteration 1. Iteration 1, I get this. Then what I do is I'll make this the start state. So actually the start state was initially maybe like this. The start state could be 2 red at the bottom. And the goal is to flip this to the top. Maybe iteration 1, I get only the top square like that. What I do is I make this the start state. And then I ask it to think about how to get from here to here. And oftentimes, if let's say you do something halfway, and you are in the right direction, it might be easier to just follow up with that to get to the final state. So in some sense, I'm doing the splitting of subtasks manually for the agent so that the agent can just take this intermediate state and think about what to do to get to the end state. It's a closer um, iteration to the closer action space in order to get from the start state to your end state. Yeah, so this was what was done in the paper. I realized that this actually much better than, just giving the what went wrong and then ask you to change what went wrong, because sometimes when you do that, the agent gets confused. It might think that, hey, maybe I should do something even more complicated, and then it gets it wrong. Yeah, but if we were to do it like that, you actually make the space a bit simpler to solve and increase the solve rate. Of course, there's a catch. The catch is that your intermediate states need to be along the path to the solution. If your intermediate state is wrong, then that's it. You won't reach the end goal. Yeah, so when I did this experiment, I think I only did it like 3 times max per problem. So if we actually could generate more and more samples, the solve rate will be much higher than what's reported in this paper. So this paper is just me copying and pasting prompts into GPT-4 because I didn't have the funds back then to use the API extensively. But if we were to use the API extensively, I'm very sure the solve rate will be much higher for this paper, right? So yeah, this is reflection. Okay, the other parts of chain of thought is actually like how we get the different kinds of view representations. So one is like how the pixels have changed between input and output, how the objects change between input and output. And basically what we do here is that we basically also give it some helper functions. Later, okay, I don't have the slide for this, but these helper functions are something like, change pixel color, rotate objects, shift objects, and so on. So I find that if we give some helper functions, it reduces the cognitive load for the LLM to come out with their own functions. And this might actually help to make the better matching better. But it comes at a risk. If you don't have these helper functions to solve the real task, then the LM may not be able to solve it because you don't have the action space. Okay, so this might be a good and bad thing. I think if I take away the helper functions, it might be more general. So again, you see this conflict between bias and true generalizability. So if we have a lot more data, it's best to do true generalizability. But if you have very little data, like in this ARC challenge, then perhaps you need to do some form of um, fixed action space or like constrained action space to make it work better. So after all this is done, I asked the LM to just describe what is the simplest input-output relationship. And then after that, write out the Python program. So I do a step-by-step thing. First, plan out how to write, then write the Python program, right? So basically, to summarize this whole thing, this is asking the LM to think in words how the rule is, then prompting it to write a Python. Something went wrong. Write a Python program. So this is actually how this was done for the ARC challenge, and it worked pretty well. Back in the days when I was doing this got one of the highest solve rates for the training set. And I think what is lacking here is perhaps better ways to do these helper functions and better ways to, right now I do every single thing for pixel view, object view, grid view, and so on. But when you don't do object view, maybe you don't need the helper functions to have object movements. Like you can actually curate your action space based on the view you give it. And yeah, I think that is something that could be done to improve the solve rate. You can also like instead of just having pixel, object, and grid, you could have other things like mirror view and so on. So again, all this I would say is very artificial. It helps to constrain the problem space a lot so that your pattern matching can work better, but it loses generalizability. So let me just draw something. Okay, yeah. So before I draw something, let's go through the results. So basically, we solve about 45% of the training tasks. But this is quite remarkable given that we don't really fine tune or anything. Basically, I just took a look at the rough problems in the training set, and like I just took a look at maybe the first 50 problems, and okay, this software is not the first 50 that I looked, but I just took a look at the rough gist of it and came up with some idea about what kind of things that I as a human need to solve it. And then I imbue this into the computer, right? So I'm very sure that if we increase the number of abstraction spaces, we will have better solve rate. You take a look over here. If we just use only grid view, which is like what DeepMind was doing, or like OpenAI is doing, like they just give it the grid view, which is the 2D grid. It only solves 7 using my method. But as we increase the number of views, like object and pixel view, we can solve one more. We just give it the pixel view, which is the colors, it can solve a lot more. Object view can solve another one. And then we combine the total number of things that has been solved, you get 50. Okay, of course, here this object and pixel, and no object and pixel view is not exhaustive. So basically, whenever like the problem is solved for the first time, I just take the view type. So it's very possible that your object view might solve more problems. It's just that I did not collate for all 111 tasks that I did. So this is just basically what solved it, and I just tabulate it. So you can see that if we were to just do a single view, all right, we actually don't really have a very good solve rate. Like, okay, we just take the proxy here because grid view is the default. If we just do just the grid view, we won't solve that much. Yeah. So this shows that having these abstraction spaces actually helps improve the solve rate. And another thing that will improve the solve rate is increased sampling. Like just sample more solutions. In my work, I only did like up to 3. But if you sample like 1,000 per problem, I'm quite sure you will solve much better. All right. And now back to the point that I'm trying to say. So this is a very crucial insight that I've discovered. This crucial insight is like this. If let's say you have this space of possibilities, and you want it to learn directly from this space, it can be quite tricky. But if we constrain the space of possibilities to a subset of highly likely possibilities, you actually learn faster. So the issue of learning right now is basically split into 2 parts. It's split into whether we want to constrain it into narrow kinds of domains so that it can learn better, or whether you want to give it the huge set of domains and it will learn a bit slower. You need more data. This one need fewer data. So it's basically a dilemma. Should we do the most general form of learning where we don't even bias it at all? Or should we bias it a bit so that it can learn better for that domain? And you not only can bias it one way, you can bias it in another way and bias it in another way and so on. And this is my view of multi-agent learning. So this is a primer. In multi-agent learning, we want varied agents with different biases and use them to solve problems. So one way I see the brain working is like we actually have various pathways to process things in different ways. And I mean, these ways could be due to the initial structure of how it was done, how the input and outputs were done for that particular section of the brain. So there's some bias based on that. And if you just use those biases to process data, like the bias could be like depth perception, color perception, motion perception. If we use that to process the data, we could get more concrete and concise ways of how things have changed. And then we could then combine them together, like combine insights together. Like what I did here, you combine the views, or you can do something like, um, um I don't know, some form of verification to select best pathway. So, or not verification, it could be majority vote. So these are some ways that you can have like parallel kind of processing, each processing done in a different way, and then just combine and consolidate the insights back together. In fact, I have an even more radical idea. So of course, this has nothing to do with the work that I've done. It's just some ideas I have right now. The more radical idea is that after you do this majority vote on combining of insights, try to solve the problem again. Okay, so basically, I don't have space right here, but let me just redraw the whole thing again. So if this is our initial space of problems. If we bias them in different ways, okay, so this is bias 1, bias 2, and bias 3. So maybe these are the different agents. What you do now is you consolidate them into, like, basically by majority voting or like some ground truth verification and so on. Consolidate the learnings. The thing is, this consolidated learning can actually serve as a way to modify your context. So let's say if you solve the ARC problem for the first try and you realize that, hey, actually, we kind of need to focus more on object view. Okay, because the object view seems like the closest to the solution, right? What we can do is we can use this insight to say that, hey, maybe we need to focus on object view. So maybe there could be a way to, focus your search efforts, saying that, oh, we need object view. So some modulator at the top or some orchestrator at the top could say that, okay, maybe object view is bias 1, right? Hey, we realize that object view is the best. Let's try to focus more on object view. So maybe object view, and maybe another one is grid view. So then you can consolidate these learnings again and see whether it reaches the pathway, and then maybe you can get the answer. So what this is, okay, this is something new. I haven't really shared this in my YouTube before, or rather, I think maybe I have shared, but not in this format. So basically, this is an iterative processing of multiple views, such that based on what the earlier iteration has discovered, you bias your search for the subsequent iterations. Yeah. I mean, this is assuming that, we have a limited kind of capacity to process things, and you want to kind of bias your search a bit based on what you discovered at the front. Of course, if you have unlimited compute, go ahead and process everything in all possible ways. You don't need this kind of consolidation. But this way of doing consolidation can also do like what we did earlier with the iterative environment feedback. Your environment feedback can come here. And then based on the environment feedback, you can maybe change your search parameters or like modify your problem to suit the environment feedback, like change the start state, for example, so that you process things in a different way for your second iteration, and you might get closer and closer to the answer, and you keep doing this. So in some sense, it's more of an evolutionary kind of approach, where you learn from the findings of your earlier generations. Yeah, I think one of the open source solutions for the ARC-AGI challenge uses an evolutionary method where it evolves the functions over generations based on how well the function fit is in the earlier generations. So that's a very interesting idea to me, and I think I might be covering that soon. This is basically a way to adaptively, learn, adapt to the situation, but at the same time, you also give room for error. All right. I mean, like, you might focus on the wrong thing, but you give, because like over here in the second one, you say, yes, it's an object view. But here I give room for error. I put a note here with grid view. Grid view is like number 2. I basically say that, hey, maybe we might not want to focus everything on it. We might also want to search a bit more on another kind of site. Right. I mean, this actually, if you think about it, this kind of seems to be more like a Monte Carlo search. Yeah, but the idea is based on what you have in your initial state, you can bias your search later. So, okay, this is a bit more of like what might be possible. Of course, you can also do like all 3 state spaces again in your second iteration and so on. So there's different ways to do this search, and the key idea that I have over here is that you just basically do it multiple times. Consolidate your learnings and do it again. This generally leads to better search results. Okay, I mean, this analogy is like this. If you do like a Google search engine, let's say if you want to find out like cars, like maybe you want to find out what about Ferraris, right? Initially you search for cars, and then it gives you all, all the models like Ford, Hyundai, Ferrari, and so on. So after that, what you can do is like you can say that cars starting with F, then maybe you have Ford, Ferrari, and then initially it's like, oh, okay, so subsequently you think like, oh, okay, I want Ferrari cars. Then you get like Ferrari 1, Ferrari 2. Okay, so this analogy is like this. You have something you want to search for. Your search engine returns you maybe only 10 search queries every time you search, or in this case, 2 queries. Okay, let's remove away Ford. Like, let's just say your search engine only can give you back 2 queries every time you, 2 results every time you query it. How then do you optimize the best approach for your querying such that you can eventually through multiple searches, I give you unlimited searches. Okay, maybe not unlimited, maybe I give you 3 searches. In that three searches, I want you to narrow down the search space as much as possible such that you might be able to find your answer. Okay, another analogy I'm going to give here is this game 20 questions. So basically, the 20 questions game, you are supposed to guess the object in 20 yes, no questions. So in your first guess, maybe ask like, is it a living animal? Is it a living thing? And the answer maybe is no. And is it um is it something you use daily? And the answer is yes, maybe. Then you can basically take whatever you learned in the past to form better and better questions for the next one. Like for example, in this 20 questions thing, like is it something you use daily? Yes. You wouldn't ask, like, is it a rocket? Because you don't use rockets daily unless you're an astronaut or something. You can say like, is it a vacuum cleaner? Then the answer could be no. So, okay, how do I put this? There's some value at doing search iteratively like this. And the more books I read about neuroscience and like memory and so on, we seem to actually not search our memory just once. We seem to search our memory, you search it one iteration, you get back some results, and then you might search again. Like that's why, when you go by like maybe your old school, then you trigger like floods of memories of like what happened in that school. Like it's not just one memory. You actually trigger quite a lot of memories, and like based on what you trigger, you might get something similar again, and you search down that pathway. Like in some sense, my theory of dreams is similar also. Like in dreams, you're trying to search down a certain pathway, and then you keep accessing like your memory to augment what you have right now in your dream. That's why your dream can transit quite weirdly. Like there's some way of preserving your current context and then keep searching and searching and searching until you get some answer. So this is actually not in my PhD thesis, by the way. This is some idea that I'm thinking of. So maybe I'll take a moment here to seek your views or like anything you want to discuss about this. So yeah.
So this idea you're getting at from neuroscience, can we really reduce it to an iterative knowledge or iterative graph traversal problem where basically you bias your search differently each time you traverse said graph, said knowledge graph, said graph of whatever. And each time you learn something from your search, you use that to iterate your search again, to refine it, to improve it for the next search of said graph traversal. You keep iterating on this graph traversal on your knowledge base or whatever you're working on to find the solution you're trying to reach. And then from there, you can backtrace your steps based on your searches and use that kind of a connectome as kind of like your guideway, your pathway to reach from your state to your end goal. Do you, does that make sense? It's
Yeah.
essentially it's an iterative graph traversal problem. You keep iterating your search query until you get the right search query, and you get the right pathway to your solution, and then you just backtrace from your current to your current state in order to reach that solution, that end goal. It's kind of what I'm getting from this.
So actually yours is a bit more fixed in the sense that you are treating the search space as like you go from one node to this node, then you go from one node to this node, and then if let's say you do it wrongly, you might backtrack here and go to another node, right? Something like that. And maybe this is your goal state. So you keep doing this traversal, and then if it's wrong, you backtrack, and then you go to another node. Is that what you're talking about?
It's one interpretation of it, but mine is more general. So essentially, you'd go forward in the graph, and you'd reach a certain end state, right? So it's a full traversal. You go from your or your start state all the way to an end state, a certain end state, based on the conditions you give to it, on when it needs to end. Then what you've derived and learned from those states you've transitioned through, you derive knowledge from them. You learn from what you've experienced and seen from this traversal, and then you apply that learned knowledge to the next traversal, the next query. So
Okay,
say
I got it. So is it something like this? So initially this is how we do a graph search, like maybe a Monte Carlo tree search or like some graph search that you do. And then like maybe initially you search this node, and then maybe you realize that um this node 2 is not the path. Then initially this is your iteration 1 search, and this is your node 2. The iteration 2 search, you might be searching more on like on other sites and ignoring node 2 altogether, because like I don't know if this is what you mean by like learning the knowledge and passing on to the next search.
Yeah, exactly. So you'll realize two is not the correct pathway. Then your second iteration, you'll focus your efforts on node one, and then you'll go down node one. You'll go down a certain pathway, and you'll have a lot of clicks. You'll have a lot of matches to your query, and you'll realize this area of the graph is very close to what you need. So then your next iteration, you'll be like, hey, this pathway is perfect. Let's go all the way through it and reach
Yeah.
the end of this graph area and see what it leads us to.
Maybe at
So,
iteration 3, you can change the start state to a promising branch.
mhm.
Yeah, so this is like what I did for the ARC challenge. I also made the start state to like intermediate state. So rather than just starting from all the way at the top, you can start from somewhere in the near the bottom.
Exactly. You can control the breadth and depth of your graph traversal and of your searches. And
Right.
you can essentially optimize your solution pathing via these iterations. And kind of like, I don't know how to describe it. It's not really hypergraphing, but it's basically based on your idea. It's the idea of like evolutionary adaptation. You're iteratively optimizing your search to
I like it.
jump
I like it.
and reach your end state as efficiently and quickly as possible. So the more you learn, the more you learn from your own searches and your own memory searches, the faster you can reach your end state, reach your solution state that you need, find that solution in your mind.
I like this idea. So actually, this is very related to like the Go Explore work that I did. Like I like explored basically the goal state, you jump to a promising start state, and the explore, then you explore randomly. So over here, one way is to bias your search via some context. Okay, that's how we bias our exploration. The other way is to change the start state, which is some form of like, you already know that this is the pathway. Put all your horsepower, all your search power all on this. I mean that's like a very good way to say that, hey, just put all my search all starting from here instead. You can also say that like rather than just changing the start state here, we can also say that, like focus on node 1A. Like maybe this is node 1A, right? Sorry, focus on uh focus on node 1. Yeah. So maybe instead of just changing your start state, we could just tell the search orchestrator to say focus on 1, and then it knows how to focus. Or more concretely, we could just change the start state directly. I mean that will be an even stronger way, because like you don't need to rely on your orchestrator understanding this. You straight away start from here. Yeah. So there are different ways to do this. I think, you know what? Monte Carlo tree search, it tries to bias the search, but with a fixed bias. You know, like you don't really change the value of it over time. I mean, you change the value of it over that search history, like that search duration. But if we want to make it more adaptive search, you change your focus over time, or change your focus or bias over time according to what works. And I think we're moving more into the realm of adaptive search nowadays, because earlier algorithms like Monte Carlo tree search, depth first search, breadth first search, and so on, all these are made in the early computing eras. When we want stability, we want a fixed algorithm so that our computers can run, because computers back then took quite some time to run, and like we don't really have ways to bias search with words back then. But with adaptive search now, I can see it happening with like LLM guided search, where you bias it with certain contexts, and then your search terms might just change based on those contexts. This is a huge step improvement over the earlier forms of search, because we don't have to search the entire search space. Like the earlier forms of search, you still search everything. Adaptive search, you can change your search space, you can change your search priority. And I mean, you can even have abstraction spaces like this, like grid view, object view, pixel view. You can have different abstraction spaces for different branches also. So it's a bit more complex, but it's also, I think, more adaptive. Like I always like to view retrieving memory as like going through, like like those memory palace. Like you have a lot of folders and they all store in different shelves. You need to first find which shelf is useful for you. Then you go to that shelf. Then you need to find which drawer is useful. Then after that, in the drawer, you need to take out that folder. And after that, then you flip through the documents to get what you need. Okay, that's like hierarchical search. But more importantly, after you find that document, you might realize, oh, holy, I need to change my search, because that document might tell me that, oh, I'm missing this new search term. Then I need to start again from the beginning. I go through my different different rooms, and then go to the shelf, go to another folder, get another document, and then like, okay, I found two pieces of the puzzle. I still need a third one. Then I repeat the same process again until I find the third one. Yeah, so I think there is some idea of continuity of what you have discovered into one common memory space. And you also need to keep searching based on what you have discovered, bias your search according to what you have discovered, in order to get a bit more efficient at your searching. But over time, you consolidate all your memories, all your learnings into this either a knowledge graph or some memory context to more efficiently bias your search. Yeah. Yeah, I think I talked quite a bit. Is that something similar to what you're thinking of, Derek?
Yeah, essentially. But mainly focusing on the idea of the adaptation and having it being deriving as much information from each search query as possible. So exploring how much. Sorry, I think someone's at my door. Give me a sec.
No problem. Okay, so I think while waiting for Derek, let me just see whether oh yeah, I'm done with this. So I'll wait a while for Derek to come back, but let me just share with you what I'll be talking about for the next part. So this part is my final work for my PhD thesis. It's called TaskGen. So this was work done at Symbian AI, and basically what I wanted to do was, can we make LMs a bit more goal-directed? So instead of using the goal-directed network that just does like pixel grids, can we make the goal-directed network of learning fast and slow do text? And that was the main idea behind this work. So the main thing is, just now we were talking about, from the start state to the goal state, and then you predict action. This was the learning fast and slow. In this case, can we do something like, if we have a certain start state, which is like maybe your task that you give it, and also you have your context. So this context could be a global context where you take stuff across tasks and so on. So this is your start state. And also your start state also includes previously completed subtasks. Let me just use the term that I do in TaskGen, subtask completed. So we give it all this stuff as a start state, and we try to predict what's my action. And in this case, the action for this kind of arbitrary kind of search space is very important. You cannot just ask it to do any action, because if you ask it to do any action, it may not be grounded to what the agent can do. Like for example, an agent that books air tickets, flight tickets, you cannot ask it to book movie tickets, okay, because it cannot do that. So it's very important to ground your functions, to ground your actions based on possible function calls. So we give it a set of functions, ask it to, using some form of, they call it the React method, a reasoning and acting framework, where, you give it observation, then you ask it to do some thoughts, and then you do actions. Yeah, so this is a form of a chain of thought. So basically, you ask it to come up with actions based on what you observed in the past, do your function call, get the result back, update your subtask completed, do the next subtask again, and so on. So you keep doing that until you solve the task. And sometimes your task can be your subtask can be quite complicated. So you can offload a subtask to another agent that has this capability of doing planning, doing some idea about what has been done before and do iterative actions and so on. So this is the idea behind the TaskGen framework, where you have an agent that keeps passing on the function calls to other parts of the system, including other functions or agents, and getting back the whole result. And through it all, the main thing is that we share our memory with each other, and we only share relevant memory. So like from the top to the bottom, we share more things. But from the bottom to the top, we share fewer things. Why? Because, if you are the CEO of your company, it's very important for all your employees to be aligned to your vision and your mission, right? Like know what you want to do, what your clients needs, and so on. But if let's say you hire your engineer, your UI designer, and so on, you don't need them to tell you, hey, I use JavaScript to do my UI. Hey, I coded this in Rust. That kind of thing. Not really needed unless you want to be a technical kind of leader. But if you just want to get something done, all you need to do from your employees is just to ask them, hey, um, what have you done that aligns with what I want to do? Like for example, if I want to do virtual reality, then the employee might report, oh, I've engineered a headset for VR. Oh, I've done a software that works on this. So basically, the employee might be doing a whole lot of different things, like searching what's the best way, like studying more of hardware stuff. But you don't need to know all this. You just need to know that, hey, yes, I have this engineering design done. Yeah, so it's a bit more streamlined because our brains cannot hold that much information. And to be honest, for LLMs, the more you give it, the worse it performs sometimes, because you might confuse it. So this is the idea of memory management. Give more to the bottom, but take fewer from the bottom. Yeah, and this was the main idea. Is about efficient memory management. So I mean, a lot of people ask me like, what's the difference between this and pure React agents? And the difference is that there's a lot more done in memory management for this. And everything in this framework was built to be as concise as possible so that the agent runs more reliably. All right. So this is what I did over like 3-4 months. I literally spent 3 months every day just thinking about this, coding it out. Yep, and eventually this was done. So earlier on, before I joined Symbian, actually I had this framework called Strict JSON. So I use this as the backbone of TaskGen. And what this thing does is that, note there's this JSON schema that is used for function calling, is used for JSON output for OpenAI models. But I find that it's very wordy. You see, like parameters, type, properties, and so on. It's too much things to tell the LLM, because actually the LLM, all it needs is just the field name and the field description and the output type. So I literally did my own pydantic because this actually can be passed by pydantic. I did my own pydantic that takes in something that is about half the token length of a JSON schema and I pass it myself. And in order not to rely on like fine tuning to get JSON out, like what OpenAI is doing, I thought of a method to get the JSON output without needing to fine tune. Okay, how? So this insight came to me in a dream. So I was thinking about this problem for a while. So if I give it a very unique locator like this, a hex, hex, hex or something, a delimiter, I can split the keys by searching for this regex string. And then once I split my keys, I immediately know my values. So what this means is that never again do I need to, mismatch of quotation marks or mismatch of these brackets. Okay, will not fail the system. Has a high chance of not failing the system. Okay, I wouldn't say it won't fail completely because I did not test it extensively, but this has worked pretty well for 20 over projects, and I'm still using this right now, straight JSON. Even with all the output, JSON output schemas and so on, I'm still using straight JSON for my own projects. Okay, so this is basically a way to get LMs to output JSON. I've tested it for like Gemini, Claude, um, OpenAI models, Llama, and it's working. So basically, even if your LM provider does not have a JSON mode, straight JSON can give you that JSON mode. Okay. Of course, it's not as extensive as Pydantic. It doesn't do complex objects as outputs, but it's good enough for most cases. So this is another way to make the token length shorter. And why is it important? So if you look at the rope paper in Llama 2, you realize that, as your token length increases, or your task length increases, actually the performance drops drastically, if we just use like, this is a rope embedding that is the native one. But of course they augment it with new parameters and so on. It can go higher, but you see, this is handcrafted. You still need to tune it for this task. Okay. If we just give shorter token lengths, it will work well with whatever tuning that you do, or right, with most tuning. So the token length is actually very important. It's not just to save costs, it's actually for performance as well. Right? So yeah. Okay, Derek, yeah, I have some time for you. You want to share what you wanted to say earlier about the search? You can do it now.
Yeah, I sent the message in the chat, but I'll go ahead and read it out. I just want to emphasize the importance of learning from the memories that you do traverse and query during your searches, so that the more information that you're able to collect from said memories that you do query, like on your first iteration or your second, the more you'll be able to bias your search and more quickly reach your solution state. Because as we agreed, the more biases you can add to your model or to your architecture, whatever it may be, the more quickly it can learn from a smaller data set or whatever the case may be. But really, what I'm getting at is that the more you can bias, the more quickly you can jump to your solution state or your end state, whatever goal you may have for your goal state, more quickly and efficiently. So you can have less searches, shorter memory traversals, and etc.
Yeah, indeed. So the moment you find the right bias and you put it in, your search will be more efficient. So I think that's a great point to add. And that's why adaptive search is better than like most traditional searches, because you can change your bias through generations. Like in earlier searches, you don't really change anything. Like you just search the entire state space. But in adaptive search, you can actually condition your search to focus on something. And it would be good if you could have like pre-biases that help to constrain the search as well. Yeah. So yeah, thanks. Okay, so I think that's all right that you have, Derek. I'll move on.
Yeah, that was everything. I wanted to finish my thoughts. We're good on that.
Yeah, very nice. Yeah. Okay, so back to this TaskGen thing. So basically, the fewer the tokens, the better the performance, and that's essentially the whole motto behind TaskGen, is to make it very, very efficient to do your tasks. And I added in a planner to just like plan out a series of steps based on some few short planning, and basically execute the steps one by one with a TaskGen agent, and the solve rate for the 40 by 40 navigation task, which is a very difficult task where the start state and end state keep changing every trial, and after 50 episodes, the walls will change. So you can see fast and slow it adapts, but it's not that fast. But if you use LMs to bias the search space, it can almost solve it all the time. I mean, it doesn't solve it all the time if I don't do some form of expert um, trajectories at the beginning. So if I give it expert trajectories, it can learn from that and solve it 100% of the time. So the key is, how can we get this expert trajectories? And one way is that your pre-training data already has the knowledge. Okay, if your pre-training data does not have this knowledge, one way to do it is to do random exploration and bias your search. So like this is always the tough problem. You see, like if you already have your answer key, like math Olympiad questions, you already have your answer key, you know when to stop your search, right? But if you don't have the answer key, you won't know, right? Unless you do verification with like you create a program and then you run the programs here to get the answer. Yeah, then maybe you can use that as a verification tool. But in most cases, there's no verification. You see, like even the real world uh wouldn't tell you whether you're right or wrong in the middle until you reach the end goal. It's like, okay, you're right. Yeah, but in between, like, okay, let me give you an example. Research to AGI, all right? People have come up with like a million ways to do it, like maybe like 3 or 4 approaches to do it. Like maybe like LLMs is all you need. LLMs as a framework. Like there are different schools of thought, like neuro-symbolic, logic-based AI, there's different ways of doing it, and you won't know for sure which one will get you there. I mean, of course, the more promising one is some form of flexible pattern matching, like in LMs. But if we don't know how to go there, like we kind of need to search a bit of each approach, maybe bias or search a bit, combine ideas together. Pretty much research is doing this kind of thing, right? I mean, I wouldn't say it's random exploration per se, but because each agent or each human has a different bias, they explore different parts the search page. So multi-agent search is actually quite important. Imagine if the whole world is just made up of yourself. Very likely we won't have the innovation that we have right now. Not to say that you are not smart or not good. It's just that us as an individual, we are too biased to our own way of doing things. Like for example, myself, I would have said that, like O1 or O3 is the wrong approach because, you don't want to fine tune too much on the correct traces because it will lose generalizability. But it turns out that actually this fine tuning might be a good thing because it helps you to adapt to your environment. Although it's a bit slower, but you can adapt to make it better for your environment. So like if you leaving it to myself, I wouldn't have explored that direction. But since it's explored, then I start to see relations with the work that I did in learning fast and slow. You know how you can train your goal-directed network using experiences. I start to see relations and I start to change my worldview and so on. So if we don't have other people researching, I probably wouldn't have come to that conclusion myself. So this is the same thing for if you want to get the expert trajectory, simply try as much as possible. And more agents try as much as possible. Maybe realign your bias once in a while. Uh, keep trying and trying, and may the best one win. And if the best approach wins, everyone learns from this best approach. Like, right now there's this whole hoo-ha about DeepSeek R1. Like, that people are trying to reverse engineer stuff and learning findings from it. So if we have things like this, we learn from each other. People might bias their worldview a bit differently, and they search differently again. They go more into a certain pathway. No, this is basically how the real world works. I don't think intelligence is one single agent. Yeah, it has to be agents that configure their beliefs, change their search base, maybe even acquire new actions based on what the environment needs. Yeah, so all these are very interesting things. And this is a good primer to move on to the next part on AgentJo. But before I move on, just a quick question or quick opportunity if you all want to ask anything about TaskGen, like anything about the architecture and so on, because this is the architecture that will be used as the baseline or as the base for AgentJo. Pause for a while. Okay, sounds good. Now we move on to AgentJo. I'm going to spend about 10 minutes here before we move to discussion. And sorry, is there a question or anything?
Um, wait. Hello.
Hi, hi, Bellamy.
I'm sorry. Yeah, I'm a little bit late, but back to this. Um, this framework, right? You're still using your memory retrieval network here.
Yeah, so in this framework itself, there's memory that is, as what I shared earlier, there's a global context where we can like share, and we have a subtask completed here as well, where we can know what has been done before. Global context just tells you like what to focus on, what's your context that the human can provide, or your functions can also update the global context.
Okay, yeah, that's it. I came a little bit late, so I wasn't here for this. Thank you.
No problem. Yeah. So yeah, these are ways to just adapt the search and so on. Back then when I created all this, is more or less to adapt to the environment. As I read more and more about neuroscience, memory, psychology, text, and so on, I kind of realized that being able to bias our own searches is actually key to intelligence. Yeah, it's becoming more and more apparent to me that we don't only search once. Yeah. Yeah, if you get the analogy, yep. So yeah, in fact, in neuroscience, there's this thing called when you are conscious, your entire brain lights up like a Christmas tree. And I think it's delta waves or beta waves. So there's a certain frequency that information gets exchanged between different areas of the brain, and it's exchanged multiple times. So why do we need to communicate more than once if we are not doing multiple searches, right? I mean, I haven't seen any text in neuroscience talking about multiple searches, but the Christmas tree analogy is quite prevalent for consciousness. Like, if we want to do this kind of like ways to search through our memories and like maybe choose the best one, search some more over there, you kind of need to communicate with different pathways in order to find out what's good, what's bad. And then you can tell each of the pathways, okay, now the focus is this, go and search again. Yeah, until you come to a consensus, then aha, yes, I should do this. Yeah, so I do think there's some truth in this, but we have to find out more by doing more experiments. But I do think this adaptive search with changing biases is very important. All right, so now we go to AgentJo. And so you can see TaskGen form the foundation of the agents, whereby we have agents that can do tasks, that have a global context that can be manipulated. We have subtasks completed that we can find out what has been done in the past. But that's not enough. For an agent to be truly adaptable, we need something even more flexible. Okay, first, we need to imbue different agents with different things for different tasks. So like, for example, some tasks you need to do planning. So we need to have a planning module in the agent. Okay, some tasks you need to, do some form of math calculation. So we need to imbue those kind of like math verification tools inside the agent. And this, I put them as agent wrappers. Later, I have a slide for this. Why I put as agent wrappers is because, as with any cognitive system, if your base is too overloaded, you will take very long to do things. Like sometimes you don't need to verify. Like if I want to generate a poem, I have nothing to verify, right? So I don't have to go through the verification pathway. Okay, but if let's say I want to do like a math problem, computer science problem, maybe I need to verify. So I add on this module that can verify to my agent. Okay, so recently there's one person on my Discord, Sebastian. He has also helped to do hooks where you can do pre and post function hooks for agent. And this enables you to help to, give certain kinds of like planning or verification biases as a hook before you do like run tasks of the agent, like agent.run. Before you do agent.run, you can do certain things like do planning before or do consolidation after. You can do stuff like that by doing hooks. Okay, that's one approach. The other approach is to do agent wrappers, whereby you give it a new functionality altogether. So all this probably a separate video. I'll talk more about it. But basically the idea is to imbue different ways of processing things into the agent in a more flexible way so that I only imbue that to agents that need it. Again, conciseness is the key. We don't want all agents to do everything. It's too much cognitive load. We just want the agent to do what it's planned to do, what it's programmed to do. Right. Second thing, multiple abstraction spaces for memory. This is important because, as what you saw earlier in the grid view, object view, pixel view, you kind of want your way of learning to be a bit more constrained so they can learn better. So this is constrained learning. And with multiple abstraction spaces, you can perhaps find the right view of learning to solve your problem. Like for math, like if you want to do circle stuff, you would likely have difficulties if you use Cartesian coordinates. If you use polar coordinates, it's very natural because radius and angle fits perfectly to a circle. So, if you have different ways to store what you learn in your memory, and you have different ways to retrieve what is relevant for your task at hand, you will solve things better, right? So this is an idea of multiple abstraction spaces. Next is the idea of adaptive learning, whereby based on what we have done in the past, or when we're doing something, like right now I'm doing a Squid Game experiment, where the agent can see other agents and adapt its own memory accordingly. And it can also reflect on what it has done before in the past and adapt its memory again. So this adaptive learning enables it to learn through the lifetime of this agent, okay, without needing the agent to be reconfigured at all. Change the memory, change the behavior. Okay, I've been reading a lot of psychology books about trauma, about pain, and this is something interesting, by the way. You can actually engineer your memories to reduce the trauma and reduce the pain. How? Just by, whenever you activate those memories, you try to replace them with something milder, or you try to uh, make your brain have the cognitive process focus on something else. Okay, that's for pain, all right? You can actually help to heal chronic pain just by thoughts. This is quite cool. But how does this relate to adaptive learning? Is because when you have this kind of memories in your brain, like when something triggers that memory, you will feel the hurt, right? So if you just change your memory by every time when you retrieve it, you think of something else or do something different, you program your memories to be different, stored differently. As you know, the brain's memories are very flexible. What you store in your brain is not exactly what actually happened. The more you retrieve it, and if you retrieve it in certain settings, you might change that memory also. That's exactly what we are doing. We change the memory via retrieval in certain scenarios, and we can actually adapt our own memories for the future. So adaptive learning has two parts. One is getting more memories in. Second is to change your earlier memories to suit the environment. So I'm not too sure whether changing memories is a good thing for AI agents because they becomes like more like humans, right? You might remember the wrong stuff. But definitely there's some merit to seeing how we adapt to new situations by just storing new memories. Yeah. So this adaptive learning is one of the core features that I'm going to focus on this year because I think it's very useful. Of course, these three are all going to be focused on. This is the alpha phase, which will last about 1 year. After that, we can move on to beta phase, which will be about 1 to 2 years, where we can have multiple agents learning from one another, different biases and so on, multi-agent communication. We can learn how to solve the environment adaptively, like basically like when you see something that has been done a lot of times. Like I think you can do this now also. It's just when you see something done many times, make the function for it. So yeah, I think it's possible to do now also, the automatic tool learning. And next, we also have stuff like we can simulate the entire population to find out like whether or not a certain action will be good. You can simulate the population out. So these are some things that can be done with agents, and I think will be very, very cool to have it. Of course, the last part is when you can simulate things so well that you can simulate entire populations in a second or within a second. And with that, you can do something what I call the dynamic agent component configurator, where you can change your agent's parameters using alpha beta testing or using some form of some optimization, like basically you try out different ways of doing it and see what works best. Because by then you can simulate a lot of things. And you can test out the changes in your mental space of simulation, even before going to the real world. So this gamma phase is more or less you'll reach super intelligence already when we reach that, because you are able to test out different configurations that enable you to perform better. Okay, so this is quite cool. But before that, we need to get all this basic stuff settled first. Adaptive learning is the huge component of this whole AgentJo framework. And there's this whole thing here that I'm also thinking about. It's called emotions. All right. Why emotions, right? I didn't put this in the framework because emotions are linked to a lot of things. Emotions are linked to how we store memory. Like we have different ways of biasing our retrieval based on emotions. Like if you think about it, you actually retrieve sad and impactful events like rejection, sadness, typically will be retrieved much more easily than boring memories or even happy memories. So there's some way of, I would say emotions are a way to tell us what's good and what's bad in the world. Like, if something hurts you, you try not to want to do it again. Or if you have been injured before, you try not to go near the source of injury again. It's actually for protection. So this way of encoding emotions in your memory can help to do prioritization of your retrieval. So this one thing. It can also help with adaptive learning because you know what memories to focus on more. If the memory is very boring, then maybe it's not the memory that you need for adaptive learning. Like for example, in my school days, I find most lessons quite boring, so I don't remember most of it. So I don't know whether it's the same for you, but what you actually study in school, you kind of forget most of it after a while. But what you remember are more exciting events like going for a conference or going for meeting this person and so on. So some form of emotion thing to weigh down how important the memory is will help with how we store the memory and will also help with how we adapt. All right. And I mean, it can also be a case whereby this emotion itself can be a trigger to do further reflection and so on. So how to encode these emotions? I don't know. Yeah. So still finding out more on that. So if you are doing psychology and stuff and you have some idea on how to program this out in AI, come find me. Yeah, I'm interested to know how to do this. Yeah. So these are some future directions that I have. So just a rough idea of what I just said. Okay, I won't cover all these slides in detail because I talked about it already. So agent wrapper is that the base functionality of your agent, you want to make it simple so that you minimize your overhead, you minimize cognitive load. Agents are modular and spawn for usage in different pipelines. So we have stuff like you can do planning wrappers, reflection wrappers, verifier wrappers, conversation wrappers. Notice this interesting thing. Conversation is not the main aim for your agent. Your agent is not built to talk. Okay, so in TaskGen also, the main thing is we don't want the agent to talk because talking is actually very inefficient in terms of communication. It's better if the agent just solves the task directly. And if you need to talk to it, then you trigger a communication pathway, like a conversation wrapper. So yeah, this is one key insight that I got. Multi-agent wrappers is you have more agents in the system interacting with one another, then you use a multi-agent wrapper. All right, so these are the agent wrappers. Abstraction spaces, as what I said earlier, you store in different abstraction spaces for what you learn differently. You can even do multimodality, and you retrieve separately from each space to solve the task. And I'll add here, you can also do multiple iterations of retrieval with different biases. So you can apply what we talked about earlier into this multiple memory abstraction spaces as well. Okay, next. Adaptive learning. So we are able to consolidate and store our reflections in our memory or via fine-tuning. So basically memory is more like instant learning. Fine-tuning is slower learning. Okay, but memory as in like text chunks and so on, like knowledge graphs, you can instantly add it in, but you need to incur higher token costs when retrieving as part of context. Well, fine-tuning, slower learning, but you may not need to put this in context. So there's benefits to both methods. O3 is a fine-tuning method. O1, O3 is a fine-tuning method. In-context learning methods are like the top one. And actually, I think in-context learning methods have a huge role to play in adaptive learning because some things you simply can't wait for fine-tuning to work before you do it. Like if you see a snake in or you see something dangerous in path A, you're not going to wait for 100 days or a million iterations of your neural network to fine-tune before you avoid that path, right? You want to avoid it straight away. And that's when in-context learning comes in, because you have the memory of the snake or the dangerous object. You will tell yourself not to go there. And again, you see emotions can be helpful for choosing what to focus on. And our human brains actually choose emotions that are a bit more fearful, more sad, in order to help us avoid immediate pain, which has some evolutionary origins, because if you don't focus on the pain or the fearful stuff, you might die. And people who die generally don't go on to the next generation, right? So essentially, the survivors of us, we kind of learn to be a bit more fearful and, encode emotions as high importance for those fearful or sad memories. And I mean, that's a problem in our modern world, but we won't go there, because that's about how to, survive in a world that makes you have stress and anxiety. But these emotions, based on like evolutionary origins, serve an important role to help us to survive. And I think this is important to encode in as well, to help to filter out the millions or billions of memories that an agent can potentially make in its lifetime. All right. So another thing about adaptive learning is that it's able to learn new skills. It's able to change its context according to the environment's needs. Like, so this part is quite cool, because we can let the agent change its global context, or add in a reflection context to the agent. The agent can bias its actions according to that context. That's adaptive learning. So you're able to learn within a task and through tasks. So you can check out the stuff that I did on Squid Game. I have one version of it on the GitHub, AgentJo GitHub. I'll link it in this video. So yeah, you can see how I'm intending to do this. I intend to extend it to multi-agent and so on. But this adaptive learning is a huge part of how an agent works and learns, because it's a huge part of how humans learn as well. Like, I do think without adaptive learning, we are not very intelligent. Like, we are only intelligent because we can adapt to our circumstances. Okay, so last slide before the discussion is multi-agent learning. So I believe that intelligence is not just a single thing, a single agent. You need to share knowledge with each other, but you don't want to share all knowledge with everyone, because then you will lose the diversity of your agents. So agents should be kept different. They should explore, let's say this is your search space. Each agent should explore different parts, ideally, of the search space, and then report back to each other. Like, and maybe in iteration 2, maybe they'll explore different parts of the search space again to focus more on humanity's needs. So like, you could also have multiple iterations of global search space that adapts to the environment needs. So this multiple iteration not only happen in a single agent, it can also happen as a global group of agents. All right. So each circle here represents the search space of each agent. Is one oval. Yeah. So, in different iterations from red to pink, you can change your search space based on shared knowledge. But we don't want to share all knowledge, because if not, everyone might just focus on one part of the search space, and you might miss out the advances in another side. Yeah, and I mean, there's also another huge thing about economy as well. So it's like, you have limited resources. You need to search according to what is needed by the global consensus. And last time I was reading this book called A History of Humankind, or like History of Our Past or something. I can't remember the title of the book right now, but it's basically talking about how humanity, before commerce came in and like money came in, essentially progress was slow. Okay, because progress only happened within a small group of people. But once we are able to trade money with one another, then essentially we can offload a lot of things via economy transactions and so on. And this significantly helps to, increase the pace at which things are being done. And then when things such as, finances, finance, debt payment and so on, like you can basically promise money that doesn't exist yet. Yeah, so this whole idea of, I can't remember the financial word for it, but basically, your banks, they loan you money, and then like you don't have to pay the banks yet, or like you can promise, like if you're a startup owner, you can promise your future investors saying that, hey, I will earn $100 million, but you don't have the money yet, but they'll fund you first. That kind of thinking helps to fuel people to to progress. And yeah, I mean, we don't have to model the economy per se, but the idea of telling each agent what to focus on based on the agent's needs and abilities versus what the collective needs and abilities are, that kind of transaction can be important to bias the search space. So that is another form of multi-agent learning in terms of aligning each agent to do what is good for themselves plus the overall state. I think that is something that can be modeled. That will be a humongous challenge to model, but it'll be very interesting to model it. Yeah. So yeah, this part about economy is not that I like it a lot. It's, in fact, I'm not very keen to have like agents like be very cutthroat to one another, like fight over resources and so on. It's more of a matter of prioritization, like what to learn or what to do, right? Okay, so before we move to the discussion, any questions or any thoughts that you have about AgentJo before we move on to the discussion? Yeah, maybe like 1 minute or so if you have anything to talk about what I've just presented. Yeah, Derek, are you saying something? Because I'm not hearing anything.
Yeah, I fixed my mic. I was just thinking maybe I think there's a slide about the fine-tuning and the in-context learning differences. Yeah, this one, the adaptive learning. The only thoughts I could really add to it might be the kind of like the analysis of what information needs to be fine-tuned and what information can stay in external memory. So I guess kind of like it, maybe not a counter system, I think it's too basic, but maybe a type of system that maybe that if you come across a certain type of memory, you could do a type of semantic analysis. If you come across a type of semantic enough times, you can kind of prioritize that semantic in your fine tuning, either data set or infrastructure pipeline, and integrate it into the fine tuning of the language model itself. So I guess deciding what system is best for that kind of fine tuning pipeline might affect how effective the agent is cohesive with the larger framework of the external memories and knowledge graphs and other systems of the framework, and optimizing that kind of gating system or whatever you want to call it, or whatever you want to implement for it, that can decide the best information to derive from its external memory systems and whatnot for the fine-tuning process, and to fine-tune the agent or the language model backend on so that it best coheres with the larger framework.
So how are you going to evaluate what is good for the larger framework? Is there a validation method or some score?
Thinking up my idea, I think the best approach might be a semantic approach. So having a type of system that can kind of do a rough, what do you call it? Rough combing of the different recent memories and go through it and do an analysis of the memories and find commonalities between different memories via the semantic analysis, and then come to a conclusion on what that semantic is, and be able to, it could even possibly do a synthetic generation. So it can analyze, basically it could analyze the memories, find the semantic that's in common with all of them, and then prioritize, hey, this semantic is really important right now in this environment I'm working in. In the long term, I can generate a data set based on this semantic that will best fine tune my language model to the environment I'm in right now. So I think the semantic approach is best, but I could be wrong. I it could be a lot simpler. It could really just be a counter system. I mean, maybe it is really a world of multi-sampling. Maybe you've run into a memory 5 times, so you're like, oh, hey, this memory has popped up 5 times. Let's shove it into the LLM and fine tune it.
Yeah.
It could be the case, but I think the semantic approach is probably the most efficient because most adaptive too, efficient and really most adaptive because you can actually analyze the memories that are very vaguely separated from each other. There's nothing in common between them that's very obvious. But that semantic analysis by I don't know, it could be an embedding model or something more advanced or complex as a pipeline, a type of pipeline system that can find that semantic commonality that isn't immediately obvious and use that to fine tune the language model and give it a much higher advantage in its environment and its larger framework.
Yeah, interesting. So if I were to summarize what you just said, there's some form of meta selector to select things that are important based on a certain context or semantics. And then based on that selector, you fine tune those memories. Is that like something like what you just said?
Precisely, yeah.
That's very interesting because then you can choose the experiences you want to fine tune based on your need. Like if your need is to eat food, right, to survive, then you fine tune memories of how to hunt for prey. Yeah. So actually, this brings me to another study that I just want to show. It's like, not show, but just talk about. They did the studies on rats, and basically they check the memories that are experienced when they are awake. So they're actually tagged with some chemical, and basically this tagging could be based on some important score. I mean, we don't know what the tagging is, but basically based on this tags during sleep, these tagged memories get replayed more. This one I think I saw it at Asimkov's channel. I have to see the video again. So basically it's a channel where they take neuroscience knowledge and make it into very nice visual graphics. And I like the channel a lot. So this kind of shows that there might be some tagging to the memories while we are awake based on how important it is to our maybe internal systems. And that system could be how important it is to our context. And I quite like this idea. Yeah, I didn't really think about tagging the memories yet, but I like this idea. Like you can choose the memories that are important to you based on your existing biases. And if your bias change, you can just, tag new memories. Of course, you may not be able to remember what happened in the past that is relevant to your new bias, but you may not need to know anyway because what happened in the past might be outdated. You can just, whenever you change your overall global context, you can tag those memories that are relevant to you right now and learn from those. Yeah, I quite like this idea. Like rather than just learning from everything, right? You already in your memory consolidation process, you already select what you want to keep.
Yeah. Now that I just think about it, we call it tagging. I just realized that my idea is very close to the Asimov video and the memory tagging, how the brain decides what to tag in order to consolidate via REM processing. So I'm now just realizing that my idea is very close to what the human mind or the mammalian mind already does. So we're probably onto something with that. But I think, yeah, the only issue is the crystallization effect that you'll find specific memories to fine tune upon. But then what happens when your environment adapts, or sorry, your environment changes? You've made the language model very precise, but very, very specialized towards a specific fine tuning of, hey, I'm in danger right now. I need to fine tune on this very precise set of memories from my environment that I've decided are very, very important towards my survival or my success. But now the environment changes, the fine tuning becomes a lot more complex because before the fine tuning could be a lot more simplified, a lot more general. You could fine tune on very basic things that are commonly agreeably good, right? Like it's generally agreed that reaching or heading towards your goal in a general way is productive, right? If I try to hyper specialize model to say, here's the exact things you need to fine tune on that'll reach your goal immediately with extreme speed, and then your environment changes, you kind of get stuck in this little trap. Now you got to dig your way out, regeneralize, and refine tune on the new environment and the demands of the environment. But those are all of my thoughts.
Indeed, when you fine tune, you will lose generalizability. So it is the case that neural plasticity kind of decreases as we grow older. I think this is similar. We kind of fine tune to our immediate environment. Actually, if the environment changes, our offspring might survive better than us because we are already fixed to certain ways of thinking. So I think there's this issue, but I wouldn't say it's a huge issue because at least in the lifespan of a human life, the environment doesn't change suddenly. It normally changes gradually. So there's some time to adapt. Yeah, so I don't think it will be a huge issue for this. Yeah. Okay, so let's oh, it's quite late already. Let's just spend maybe, if you all don't mind, another like 5 to 10 minutes for our discussion. Then we can conclude the session today. Yep. I think today has been great. I really enjoyed the discussions and so on. The main thing is to build the system. Okay, I don't really care about what I did in the past. I care about what I'm going to do in the future or what we are going to do in the future. So these questions are to guide us to reach the end state of fast learning and adaptable agents. So first, I keep criticizing about reward in my presentation. The thing is, sometimes, reward is still needed. And the times that reward are still needed are when you cannot define your goal in words or you cannot describe it. So like maybe locomotion, how you balance yourself, sometimes very hard to describe as a goal. Like the goal can be balance myself, but their states can be a bit hard, like top or like angles at 12.5 degree of my elbow and so on. Like very, very difficult to say this in words. So in cases like this, maybe reward is still very useful. So the question is, how do we combine both reward and goal-directed learning? And like I have an approach for this. I'm just going to share mine, then I'm going to ask for opinion. So it's like high-level planning. You can use words typically. Yeah. But lower level execution, you can offload to a module that perhaps is trained by reward. So an example of this is like if your robot wants to go moves forward. All right, this is your action, right? Then you actually use maybe the PPL algorithm to move the limbs forward. Yeah, so this is an example of what I mean by this. Like high-level planning can use like the React framework to do the task decomposition and so on. Choose the next action based on observations and thoughts. After that, at the bottom level, you use reward to train it. Okay. Any other comments for this? Okay, if not, the next one. Is memory always fixed or is it changeable? I would say that memory is changeable. And there might be a benefit for changing memory is so as to adapt to situation. Right? Basically, when your environment changes, or adapt to environment, when your environment changes, your old memories can, if you can just change the context a bit, it'll be more relevant to your task at hand. So maybe your cognitive load to identify what's similar to your current situation will be reduced when your memories are changed to what's similar to your current situation. Right? So this is why I think the brain does memory changing during retrieval to make it easier to retrieve such memories in your new environment. Okay, but of course the cons is that, like the pros is that easier retrieval. The cons is inaccurate memories. Yeah, but the thing is, as long as you don't change, maybe just change superficial parts of the memory. Or I don't know. So we have to investigate more about this, but there's some idea about how your memory, after stored, it can adapt a little bit to your changing circumstances. We have to do some experiments to see whether is it beneficial to do that, or is it better to just keep everything as how you perceive them when you store them, right?
Yeah, I think emotions are going to play a huge part in this memory retrieval process because essentially what it is memory compression. You're basically compressing the unimportant parts of the memory to make it faster for retrieval time. But the emotions itself are still the same intensity. If you've ever noticed that, um, what I've been through, what I've noticed is that my emotions are the most intensive part of my memory. So the nuances of the memory itself, the location, the time, sometimes the faces involved, you see those things fade. Your memory becomes very reduced and compressed. But you never forget the emotion. You still feel the intensity of maybe the embarrassment, maybe the anger, someone really ticked you off, they said something really mean to you. Maybe you felt an ecstasy in the moment. Maybe it's your first time falling in love with a girl you really like. That emotion's intense. You remember that emotion. I think the emotion is kind of the knowledge representation of what's important about the memory. Like the emotion represents, hey, this is a really good time. This is something you should remember how good this was. Whatever you did here was really good. It felt really good, right? It basically, I think the emotion itself is a compression of the knowledge summary of that memory, of that experience. So not only do the memories get compressed, the emotions themselves allow for that level of compression because the emotions themselves are essentially compressions of the importance of that memory, of all the knowledge stored in that memory that makes it so important. They get compressed to a single emotion of, hey, I felt really good here. You don't really need to remember all of the nuances of why you felt so good. Why did I enjoy this so much? Why did I hate this person so much? It's just very quick retrieval. It's very quick. Hey, this is bad. You hated this. Don't do it again. Simple. It takes 3 lines of memory, 3 lines of sentences. That's it. Done. You don't need to philosophize and sit down and contemplate it all day. I'll say this: self-reflection is very, very important for deriving knowledge, and becoming more intelligent. But at the same time, when you're crunching memory, memory is a numbers game, in my opinion. It's all about the sampling. It's all about the efficiency, how fast you can hit your goal state, your end state. At the end of the day, emotions are very powerful for that. They allow you to compress a lot of knowledge into a very small summary of information.
Cool. Yeah, I do agree with you that the emotions retain, whether is it important or not for that memory. Uh, but just so you know, like I recently read a book called The Memory Code, and it's possible to actually change your emotions of the memory by, like, once you retrieve them, you tell yourself, oh, actually it wasn't as bad as that. Like maybe the other person had some issues. It's not exactly your fault. You can actually condition yourself to reduce that emotion and make sure that after you do it many, many times, that memory doesn't haunt you much anymore. Yeah, so it's possible to actually change your emotions of the stored memory, but it takes a lot of effort. It's not easy at all. So yeah, I think we have to bear this in mind, that the emotions can actually be changed, the emotional tagging to the memory. Or rather, you might create, maybe it cannot be changed, but you can create new memories with different emotions. And then that might, if you swamp it enough, that might override your original negative emotion memory.
Yeah. I think that actually might be important because, like, by way of an example that he said, just because that girl from high school broke her heart bad doesn't mean the next time you meet someone, like, you'll need to experience that much pain or emotion. You need to, like, kind of discount it, I guess, so you don't under exploit or in your search, if that makes sense.
Yeah, definitely. So I think actually emotions play a huge role in the way we view memories, but it is possible to change it. So just I think even the Bellamy you mentioned about the high school girl thing. So that is something that you don't want to let the initial bad experience affect your subsequent one, right? Like, so it's
Yeah,
possible to override your stored memory, but with a lot of work.
exactly.
Yeah. So I think in an agent, the memories itself, right now we don't tag them with emotions, but if let's say we tag them with emotions and we allow the agent to, maybe consciously change the emotion if they need to, and like maybe even like subconsciously change the facts of the memory. I think it is fine because if you change the memory to make it more similar to your context, you actually have a better chance of getting the right retrieval, right? So we explore stuff like this. But there should be more than one way to store the memory. So it's like even if you change the episodic memory of what happened, some facts, like for example, do not go into a river filled with crocodiles. You know, some text like this, you can store as some form of semantic memory that, you know, even if you retrieve the memory and you change the episode, your semantic memory remains intact. So you don't go inside a river of crocodiles. You know what I mean? Like, you can change episodic memory maybe, but you might want to stick with your semantic memory. So, you know, there's some safeguards. So the episodic memory might be easier to retrieve based on similarity to your scenario. Like, for example, if your memory is in school A, now you transfer to school B. But the learnings in school A might also apply to school B. You know, then it's okay to morph your memory to, like, okay, instead of school A, I morph it to school B. I mean, it still helps you survive. Okay, why not? Unless that memory is totally irrelevant, then what will happen is you will typically put a decreased importance in that memory that didn't really help you in your current situation. You probably won't retrieve that memory again. Yeah, or very low chance. So quite interesting how your memory's importance gets changed according to your context. I think we need to explore this a bit more. Yeah, this is a very good adaptation mechanism actually. Okay, yeah, before we go on too much into this, because this is very interesting, we need to end the session soon. So this next one is, how do we do adaptive learning by reflection when we do not have the ground truth? So, you know, in a lot of papers, they ask the model to, like, do a task, reflect, and then take learnings and do the task again. And this reflection, also some people call it reasoning, like basically like you can find out what uh rules, what patterns to take note of. The thing is, if we just ask the LM to just reflect on its own, or like do reason why do you think these 5 instances end up like that? I mean, based on my experience with the ARC challenge, if the LM doesn't have some form of bias in the pre-training data that can help to identify things, it typically won't get this kind of reflection. Case in point, if you want it to reflect on, like, on the color like green, but you know, your training data is only on red, you know, it's very unlikely that you can reflect anything meaningful about a new color. Yeah. Yeah. So it's you kind of need to make sure that this reflection that you have, you need to ground the reflection. So how can we ground this reflection? Typically, you can ground it in the realities of the world. Like, for example, physics. You can ground it in physics, like objects will move down instead of up. You can also ground it in terms of ground it in expert trajectories, or like previous kind of formats, all right, of reflection. So this is a huge piece of work, by the way. Like, people are trying to figure out how to do reasoning traces and how to best, like, ask the model to come up with their own reasoning that is more suitable for the world itself. I don't think we have solved this problem because LMs are inherently pattern matches, garbage in, garbage out, right? Like, if you want it to get the right reflection, in fact, what do you mean by right reflection? What do you mean by right reasoning traces? Do humans even do reasoning traces? The thing is, I don't even think humans reason very well. Like, we just back reason most of the time. Like, we do the action and then we try to reason why we did it, in the hopes that this reasoning memory can be used in the future to help us do better actions. So essentially, this is a very radical view. Reasoning is not as important as how it will affect our actions next time. So, you know, there's a million ways to do reasoning. I don't care whether the reasoning is correct. The main thing is whether the action will lead to your survival next time. That's the main thing. So, you know, there's a lot of human artifacts like superstition, right? You must wear red during auspicious occasions, or you must do certain things before, like, good luck can happen. The thing is, most of these things don't really work. But the thing is, if it has been done before in the past once, and then people have seen it seen that it was successful, maybe they'll say, oh, I need to wear red because if not, I'll be unlucky. You know, they kind of do some reasoning like this, but the reasoning is not correct. But you know, it doesn't help you if it doesn't lead to your death. So, you know, you can still keep those reasonings. Yeah.
Actually,
So
I beg to differ here. I feel like it's the other way. It's like if you actually go and study it, you try to figure out the statistics. Maybe actually my understanding is that does not help at all. But it's the psychological biases of human just makes us just to think that way, even though it's not rational.
So how do we store reasoning that? Like, do you have an opinion of like how we come out of it?
Like how should I say? I'm not sure the ground, like the core reason of that why that's the case, why this kind of behavior emerges, but it just somehow is like just okay, it might be driven by the angle that you want to survive, that's for sure, right? But I also agree, but this reasoning, um I think our opinion differs here because of I don't think it ultimately helps to help the survival, but humans still nevertheless want to find some way to survive. But so this is like they're just trying to force their way of thinking. Then somehow there's this kind of biases, which statistically speaking does not help, but it's kind of like a defect of how we think. Yeah, it's like a defect because it's irrational. Yeah.
Yeah. I mean, people all along want to find out reasons so that they can find out like things like cause and effect, try to prevent something bad from happening because you know the cause.
Yeah, exactly. But the causation is and correlation are different. So, like people don't really think thoroughly whether it can really help. But somehow on superficial level they think it can help, but maybe it doesn't really help. But we because we intrinsically we are not entirely rational, so people uh still use this way to try their best to maximize their survival, you know.
What if I told you reasoning biases your actions next time? Like based on how you reason, like for example, oh I must not walk under the rain. Okay, like maybe next time there's a lightning strike because of your way you reasoned before in the past, you avoid walking in the rain when it's raining, you survive. Like so basically there might
I get what you mean. So you are talking about another scenario where somehow by pure chance they help.
yeah, correct.
I see. Okay.
And
Sure. I mean, sure, but then if you don't really think thoroughly about it, maybe people will think, okay, then it helped. So there's some kind of causation there. Then they just use it as a strategy for survival. Yeah.
yeah, in
So,
fact, oh yeah, sorry, Derek.
No, finish your thought. I'll go after you. It's fine.
but I think this actually tied back to one of the observation. Okay, not it's not about not my opinion, but it's about the fact that you said the intermediate ground truth sometimes doesn't really matter, right? Because if it leads to the correct angle, then the intermediate correctness doesn't really matter.
Yeah, I mean it's not as important as how it biases our
Yeah,
what.
and if I don't know if I think I've seen some commentary on the DeepSeek R1 model. They actually find out something similar. Like that's why they get rid of process reward model, which help you to check in intermediate steps, but the end result is still good. Yeah, so they are also saying that you do not need to waste so much compute and resources to check the intermediate correctness, but their end result is still quite good. So I guess these two way of thinking of the result somehow align. Yeah.
Okay. Well, when we say ground truth, are we referring to any type of validation, or is what do you call it? Environmental feedback separate from that ground truth? Is ground truth its own thing, and environmental feedback is another type? Because the only way I could see moving forward with this without any type of validation or ground truth would be that constant environmental feedback. The more feedback you can get from your environment, from testing, you can test actions, have a type of hypothesis, see, hey, this and this happened, and then you can get your cause and effect from that. You can derive a kind of graph of cause and effect from constant testing, constant hypotheses, constant environmental feedback, and see what actions cause what behaviors and why. And even then, I mean, to go to Zhang's point, I mean, with the DeepSeek validation, it might not even matter how you correlate it, or like what you think is causing it. That might not even matter. What matters is you just summarize and you understand what your cause, what action you did, had this effect, and that's all that matters. That might be the baseline of all intelligence. You might not need anything more than that. Everything else might just be a byproduct of that. You just need to understand, hey, I did this action and it caused this behavior. I'm going to remember that. And from there, you can build multiple axioms of knowledge. You can start with basic cause and effect, and then you can start building layers of mathematics and reasoning and logic just based on those basic cause and effect observations you had.
Okay, I quite like the what you said, Derek. So like you have input to output 1, observation 2, you have input to output 2. So basically all this you don't know why it's done like that. But what you can do is you can form a form of reasoning to find out common patterns, and then can use this to ground future actions. So it doesn't really matter whether your reasoning is correct or not. I mean, you can refine your reasoning later, but at least it's a heuristic based on multiple observations. It's a heuristic to see how things are happening. Like it's just a way for you to like invest. It's like you're your own hidden scientist, right? You're trying to figure out what's happening. You just kind of a broad heuristic, and this heuristic doesn't need to be correct. It can be refined through time. And so even without the right grounding, as long as what your heuristic is doesn't contradict your input to output, I think you're fine. You can reason in however way you want, as long as it doesn't contradict your initial observations. Did I get your point right?
Yeah, that's pretty much what I'm saying. My biggest point to reinforce this, I will say, is just think of the Neanderthals. I mean, we found fire some way, and I think we didn't have any, understanding of logic or mathematics. We didn't do these back tracing of reasoning to validate our own reasoning. There was a caveman. He saw lightning strike some tree or whatever, and he saw it burned, and that was it. That's all he saw. He saw input and he saw an output. He saw fire, and he said, "Hey, I wonder what else could cause fire." And then he started to think about it, and then the guy found some flintstone, and he sparked it, and he saw it cause fire, and now he has warmth. That's all. That's all the caveman cares about. All he cares about is this object causes this fire. Now I have fire in my inventory. That's all that matters. That's all the caveman cared about. That caveman had no understanding of reasoning, back tracing, logic fallacies, and the logic validation. All that caveman cared about was this flintstone causes this fire. Cool. I'm gonna use that now for whatever I want.
I like this view. I mean, it actually is very similar to modern science. Basically, the scientific hypothesis, you seek out experiments, you conduct experiments to test whether it's correct. So once you observe, like the caveman observed, like the fire started based on like a lightning strike, tries to try to re-engineer the situations, try to see, oh, if I just create friction, is it enough? Or is like, okay, if it's lightning, maybe I put a kite fly in the air and see whether I can conduct electricity to light up a wood and so on. So it's something that I think we humans do very well. If you are very interested to see whether something works or not, we will figure out ways to test it. And this biasing of our search space too, we can even bias our observation space by putting ourselves in the right scenarios. So it's quite cool. Not only can we bias the search space of our thoughts, we can also bias our action search space just by wanting to do something. And I think this might be the way that we like refine our reasoning and so on. So the reasoning might be wrong, no problem. But as you do more and more, it gets closer and closer to the correct reasoning. And it doesn't really matter if your reflection or reasoning is correct all the time. What matters is that it's enough for you to survive. Yeah. So I think that's an interesting thought. Yeah, Bellamy, you've been
Yeah.
what you want to.
I guess I just want to say, like, what if our input outputs become much more complex? Like, yeah, we start from nothing to fire, but then fire to the light bulb. I think we do need some intermediary results to try to be correct or prove correctness. We can't just like maybe form a reasoning to find common patterns because we have these super complex spaces.
Well, what I am saying is that the input output is what matters. I'm not saying you don't need the intermediate steps. I'm saying the intermediate steps are emergent of this basic rule that you're following. You start with figuring out fire, then you can use that fire to figure out how to do something like I don't know, produce energy or whatnot, right? Maybe you figure out fire. No, this is a great example. You figure out fire boils water. Then you use that basic input output logic to figure out, hey, this boiling water becomes steam. You figure out that logic or that basic observation to figure out, hey, this steam pushes things. You figured that out.
Right.
Now you build upon the knowledge in axioms. Now you can use steam to create a device. I forget the name of the device. It's the Helio something. It's the very cool ancient steam device. You just boil the water inside, spins the wheel, and it goes super fast. Boom. You have a form of energy transfer. Then you just keep building up. Then you use energy transfer. You can use that to power a light bulb or electric generator. It's a very basic rule. It's input to output, very basic observations. And all these observations build up over time, and you could build a graph or an axiom or forms of logic that all build upon each other. You're always building on your knowledge. It's such a basic rule, and you can lead to such beautiful results. It's all emerged. Yeah.
Yeah, I was gonna say, and somehow we could converge on maybe what the right reasoning or whatever that may mean is.
I think the scientific knowledge comes after the engineering. That's my opinion, and I think a lot of engineers have that opinion. But I think it's very valid because we didn't figure out the science behind things until we figured out the engineering itself was possible. We didn't figure out how the stars moved until we figured out how to view them in the first place. We figured out how light comes into our lenses and interacts with our eyes and figure out their movements. I think only then, when we had the engineering to observe them, that we actually started to understand the science behind them. I think that's the beauty of following this basic rule of observational hypothesis testing, or just basic observation and environmental feedback.
Thanks for the discussion. Very interesting. So I do think reasoning can be updated over time, and one reasoning can lead to even more reasoning. And I think this is also a point that I want to make is like, O3 fine-tunes on its own reasoning traces, successful reasoning traces, likely. And this actually can lead to them, like if they master one part of the pipeline, they can actually master more parts of the pipeline because your first reasoning might help it to solve more and more things. So I think this is a very good thing that we build on knowledge that we have stored before. O3 just demonstrates that you can build on fine-tuned knowledge. Yeah, there are other ways to build knowledge, like traversing a graph, storing knowledge in other forms, like external memory. And one big thing is that, you don't need the reasoning to be perfect. All you need to do is that the reasoning validates what you have seen. So you don't really want to reason things that cannot happen. Like for example, if I'm drinking water, I don't want to reason, oh, the world has okay, sorry, that's a wrong example. But let's say you want to say like, okay, from fire you can heat water. You don't want to reason that, oh, the gods made something change in the environment and then the water is formed. So it's very like very, very okay, maybe okay. I have to refine my view on that. Even if you invoke the gods in your reasoning, as long as you invoke the gods at the right time, it can still be a good reasoning. But yeah, hard to give you an example for this because because anything that's flawed, as long as it's flawed at the right time, it can be correct. That you may always think that, hey, we are actually removing oxygen, that's why we stop the fire. What if it's not oxygen we're removing? What if it's some particle that's inside oxygen itself, but we think it's oxygen? But by the way, I still think it's oxygen. But the thing is, I'm just saying that if we come up with a wrong reasoning, as long as it is consistently applied at the right time, it can be the correct reasoning. Yeah. So
I wouldn't call it wrong reasoning. Like if the reasoning of your framework to explain certain phenomenon, it can explain within a certain constraint, then within this constraint, I don't think it's wrong, right?
yeah, you may not have the full picture. Just like Newton, he has 3 laws of motion. So it turns out that actually it did not account for planetary motion. So that one Einstein came up with the law of general relativity. So it doesn't mean that Newton was wrong. No, actually he was right for the problems that he considered. Yeah. So the thing is, reasoning itself may be like correct. I mean, in terms of the Newton's laws, Newton was actually not correct because his loss is not the actual motion. I mean, who knows? Maybe Einstein is wrong also. Yeah.
I understand your point. I agree, but I'm also trying to say that I tend to view the framework itself and the reasoning are two separate things. You can reason based off of this framework, like the classical mechanics or quantum or whatever, right? But the reasoning itself, it has to be like A leads to B, B leads to C, that the logical reasoning itself need to be intact. But there are multiple equivalent framework that can explain the same thing, right? Yeah.
Correct. So that's why I say the actual reasoning itself doesn't really matter. What matters is that it biases your actions sufficiently enough. So in this case, if you get the right deduction that fire leads to a heated water, regardless of how you think the fire hits the water, as long as next time you want a hot cup of water, you know how to use a fire. I think that's enough. Yeah, so that's my point. Yeah, I think reasoning itself, you don't have to get too nitty-gritty with the accuracy of it, as long as it helps with your end outcome. Yeah, and so I think that's why DeepSeek could work just by looking at the end end outcome, because as long as the end outcome is correct, no matter they say wait in the middle, as long as it gets the outright output, it biases your decisions accordingly. That's enough already. Yeah, so we can talk more about this. I think this is an interesting thing because the way we bias our reasoning or reflection by like asking the framework in which you reflect in is very, very important to get good reasoning or good reflections. Like just asking for reflection directly may not get you the answer, but if you have a certain framework to reflect, like do macro reflection, then micro, then after that analyze accordingly, you might get better reflections, which might give you like the better associations of fire to heat water rather than like fire to I don't know, to invoke gods and then heat water. Yeah. So if you have the right framework of reasoning or reflection, you might be able to get better and faster ways to get the right reasoning. And as I said, there's no need for the reasoning to be right. It just needs to be enough for you to bias your actions. Okay. Of course, this is my point of view. I know I will offend a lot of people who are doing logical reasoning by saying this, but this is my point of view. Yeah. Okay. So, oh my, it's quite late already. Let's spend the last like 5 minutes on the last one. How should multiple agents interact with one another? So I think this one is basically interact on a need-to basis. So like people recruit agents, they want to do stuff with them and share knowledge. So again, there's going to be some form of an economy where agents will trade with one another. They can trade their time, they can trade their expertise. And based on that, you have small groups. Small groups can also trade with one another from bigger groups. And so with this way of doing some economy, we are able to get an allocation of resources. And these agents can improve themselves. If the information is good enough, you might share through social media or something to share with a larger group. But I don't think the agent should share everything about its life. What it should share is basically you need to share only what is needed for the global context. So you think of TaskGen, about how the functions and the inner agent share only what's required based on the task that is asked of them by the meta agent. You think about that in the global context, maybe someone employ you just for doing Rust programming. You should only share what you did for Rust programming. Or you share what you did for Python programming. Don't share anything else because it doesn't really benefit what is needed. Okay, so I think there's some way of defining the scope of an agent in a group setting, and the agent should only share what is needed based on that group setting. So in that way, we avoid contaminating everyone's life experiences with one another. Like I don't want a case whereby agents share their entire life history. And so like this agent may be very timid, doesn't like to do a lot of things. They share these experiences with everyone and everyone becomes very timid. That's not a good case because we still want explorers, we still want people with different characters, and you don't want everyone to be like not. I mean, you basically don't want to bias everyone to be the same thing. Yeah. So I do think there's some economy going to be involved here. Economy for for allocation of agents, allocating time, expertise, and you share only what is needed. I already wrote that down there. Yep. So I think these are going to be important facets of multi-agent systems, and also through one generation to another, it has come to my attention that we can inherit memories from our parents. Yeah, so basically they have done experiments on rats. They took the father rat and they shocked the rat whenever the rat experienced some light. And even without meeting the father, the child rat was scared of that light. Yeah, so basically this is not natural for rats. So it is likely that this traumatic experience was passed down through the sperm of the father rat. And this was quite significant to me because I didn't know that memories can be inherited from the parental generation. So there might be a way to pass down knowledge, especially traumatic ones, down to the next generation. And this actually can help with survival. But in the modern day and age, it can also lead to greater stress and anxiety. And yeah, so there's another pathway to this that those spiritual well-being books will talk about. But the idea is with these traumatic experiences passed down from one generation to the next, it could actually lead to better survival. So there are ways to transform memory like that. Of course, there's also intergeneration memory transfer via behavioral imitation or books and knowledge and stuff like that. So there are many ways to do that. So it's very interesting to investigate this. But one key thing is passing down of knowledge is important. And with multi-agent interaction, knowing when to give your knowledge to other agents is also important. You don't want to flood everyone with all your knowledge. Okay, so I'll just give maybe a 1 minute. You all have any comments on this last point?
I know I shared some messages in the Discord talking about how agents can learn to interact with each other, or how agents form their own rules and triggers for interacting with each other. So essentially, you'll have agent A goes down a certain line of thinking, and maybe something in that line of thinking triggers another agent to come in and maybe interact with agent A or override it, like, hey, I noticed you're starting to think like this. Hey, maybe let's consider a different line of thought. You know what I mean? These agents can interact with each other and start to learn when they should butt in. They can learn the rules for interacting with each other that works best and provides the best result. But how that will look like is very vague because I don't really know. Maybe it's symbolic programming. You program some logic and some rules as to how the agents interact. Maybe it's adaptive. Maybe the agents are given tools on how they can treat each other and how they can learn to interact with each other and deliberate amongst themselves and decide how they interact with each other in a controlled environment. I don't know how it looks like, but I think it'd be a very cool experiment with that kind of like agentic reasoning, or how would you call it? Agentic deliberation and dialogue.
Very cool stuff. So actually all these are very exciting to experiment with. There's still a lot more to figure out. I'm sure through the next year or this year, since this year is the year of agents, I'm sure we'll have more exciting papers to talk about as well and more exciting experiments to do. Yeah, so I think with that, let me just end the session. I'd like to thank again my professor, Prof. Mehul Motani, for letting me explore my interest during my PhD. And that's how I can come up with all these concepts and even the plan of AgentJo, where I intend to continue to incorporate the insights of what I gained from my PhD, basically the goal-directed memory-based learning. I try to bring it on to a larger scale, larger level, and hopefully we can create the fast learning and adaptable agent systems that I'm thinking about. Eventually, I hope to go into robotics as well. So this could be employed in forms of robots, right? So, but after all, I seek to emphasize that I am still pro-humanity. I don't really want AI systems to be used for bad stuff. So I emphasize a lot that this system should be something for the good of humanity, which means that don't put an action space that can, potentially kill humans and so on. Yeah, so that is quite important. And yeah, with that, let's just like to say that if you're interested to help to build this together, the GitHub is down here, github.com/danchongming/agentjo. And yeah, do join the Discord as well if you're already not there. And there's also an AgentJo logo design competition to, help to give a nice logo for the framework. So I actually intend to extend it 1 more month to end of Feb. So if you have any nice designs about how AgentJo should look like, please put them on the Discord. Yeah. So with that, thanks so much for coming today, and see you again next week then. Okay, bye.